So yeah, I'll introduce Paul. So welcome Paul to the invited talk at the Vision in AI Lab at IISc. So yeah, so Paul Gavrikov is currently a postdoctoral researcher at the Tübingen AI Center in the group of Hilde Kuna, right? And he before this he finished his PhD in Janis Kuiper's group at Hochschule Offenburg and University of Mannheim, and hopefully will be defending very soon. And I had the great pleasure of writing a workshop paper with him. And yeah, he's an amazing, a very smart guy. And today, I guess we'll be talking about his recent ICLR paper. So yeah, Paul, you have the stage.
Okay, thank you very much for the great introduction, and it's a great honor to be here. So today I want to talk about feature biases. This is mainly about the ICLR paper, but there's also like some preliminary works that we did in the past years. And I guess we can skip the about me part now. So I want to say like the title of my thesis was Decoding Robust Generalization Object Recognition. So I'm really interested in robustness, computer vision. Obviously these days when you do computer vision, it also has a little bit of multimodality inside, and this will be like the primary scope of today. And I'm also interested in interpretability. Now, I put interpretability in quotes because typically when people do interpretability, it's toy examples or it's like more explaining what your model does. I'm more interested in how the model fundamentally operates and like what kind of stuff it's working on. So like understanding the algorithm behind the model a little bit better. And so I want to start this talk today by giving you a little bit of overview of some of the works that we have done, also the stuff that's in my thesis, and then I kind of wrap up with the ICLR paper. So the first part will be about generalization, and then it's more about interpretability. So I think you're all familiar with the problem of distribution shift. This happens in any kind of machine learning model, but we also see this a lot in computer vision. We're training our model on some kind of nice images of cats, for example, which are perfectly lit, and the images are of great quality. And then at test time, we observe new samples, which might be a little bit corrupted. So the image might be blurry, it might be foggy, there might be some kind of weather effects happening, or like noise from the camera, for example. Or we're no longer dealing with photos of cats, but paintings or 3D animated characters or like sketches and cartoons. And obviously, as you can guess, like most of the models, if they're just trained on images of cats, they will not recognize the samples that I'm showing you at test time, or at least it's a big problem in computer vision. And you can argue that the top part of the test images that I'm showing you are more about robustness. So this is still like the same cat, more or less. It's just in different scenarios. So your model should still be able to recognize this. The bottom part of that, I would consider this out of domain. So depending on who you speak to, this might be out of scope for robustness researchers, but I think it's still like an interesting problem from a user experience. When you train a model to recognize cats, it should kind of recognize cats in all kinds of scenarios. And so one of the questions is like, why is the model not working? Why is it not recognizing cats? If we train on this cat, why is it not recognizing the other ones? And the reason here is, or like partial reason for that, is that the models are so-called cleverhances. And this is actually a term coined after a German horse. And this German horse was said to be able to do simple arithmetic questions. So you could, for example, the trainer would ask the horse, what is 2 + 3? And the horse would stomp its hoof 5 times in response. And as you can imagine, horses cannot really do math, at least not in the way that we humans can do. And what the horse was able to do is like it was able to pick up how the crowd and the trainer reacts, and then it would just stop stomping its hoof. So the horse gave the right response, but for the wrong reason. And the same thing happens in computer vision models. They are also giving us the correct responses, at least when distributions are similar. But if at test time the distribution changes and these poor features are no longer there, then the model is just hopelessly lost and it gives us the wrong responses. And there's a lot of examples of this happening in literature. I think that probably the best one known are adversarial attacks, where you can just take an image and you slightly perturb it and it causes the model to not only give you a wrong prediction, but it's also super confident that this wrong prediction is the right answer. Then there's also a ton of research on ImageNet models, which has shown that ImageNet models very much look at watermarks, if there are any present in the images, instead of like recognizing this bird here. Or they're also very much influenced by the backgrounds of an animal. So in this case, you could say you recognize the birds because it's a bird, but in that case, in the case of ImageNet, it also recognizes it because of the composition with the backgrounds. And also one thing that kind of achieved a lot of interest was the texture bias, which shows that models really look at the texture of an object and not so much at the shape of it. So for example, here on the image on the right, this looks like a cat to most humans, but a model will tell you that this is an elephant because it kind of looks at the texture that is placed on top of the cat. So overall, if you have some kind of way to understand what the model is looking to, I would argue that it's relatively simple to detect when a model is doing wrong. So if it, for example, if it looks at the watermark, it's quite easy to understand that this is not the correct feature to use. But for the reverse, like what is the correct feature, that is a much harder question. So it's not super simple to define how to detect a bird, for example, in such a way that your rule only applies to birds and no other objects, and it captures all the birds and all the conditions that can happen during train and test time. And so there's one line of research that said, okay, we don't know how to define these features, but let's look at what humans are using. How are humans recognizing the world? And maybe that is a better vision system to get to models that generalize better. And so my thesis was partially also about this. And we have seen that robust models, which are examples of models that generalize well under adversarial attacks, tend to be more human-like. So they use features that humans use. So what you can see here are 3 models, ResNet 18, ResNet 50, and Wide ResNet 50, all trained on ImageNet. And on the x-axis, you see the strength of adversarial training. So the larger this number, the more robust your model gets, and 0 is like the baseline without any kind of robustness intervention. And there are 2 plots interesting here. The first one is this Q-conflict accuracy. This is this shape bias that I just showed you with the cat, which has elephant skin on top. If you would measure this for humans, they would be at roughly 100% for this. And as we increase our adversarial robustness, we actually also tend to get models that become more human-like in this aspect. The second part is error consistency. So you can measure if models make errors, are these errors the same as for humans? And this is also something that increasingly becomes more human-like the stronger your robustness gets. So one may say that there is a correlation between robustness and human vision, or thinking or seeing like humans do. Now, robustness is actually a very nice topic. It's very theoretical, but it also has a couple of nice applications. We have also, for example, seen that robust models are better calibrated. So what I mean by that is that if a model should know when it doesn't know. And in other words, if it gives you a wrong prediction, the confidence in this prediction should be super low. And if it gives you a right prediction, it should be confident in this. And here I'm comparing 2 models, a non-robust one and a robust model. And I'm plotting the distribution over the confidences in correct and wrong predictions for both clean samples and samples under adversarial attacks. And what you can see is that the non-robust models on the top, they have a peak at 100% confidence. So whenever they give you a response, they're 100% sure that it is correct, even if it's wrong. And that is something that we don't want. If we switch to robust models, on the other hand, these tend to have more bimodal distributions, in the sense that when they give you a right response, they're kind of confident in this, but if they're giving you a wrong prediction, then the confidence is very low. And this allows you to kind of, just by looking at the confidence, to estimate whether the answer will be right or not, which is, of course, a very nice thing to have in practice. And this arises just from this robustness intervention. So based on these two papers, you may now ask, okay, does the reverse also hold? So we have seen that robustness kind of implies a better alignment with human vision. So at least if we make our models more robust, they also become more like human vision. And we have seen that if we make our models more robust, they become better calibrated. So then the question is, can we also look at the reverse direction and say, can we just make the models see more like humans and then get better robustness and maybe also calibration? The reason why you would do this is that to achieve robustness, the training cost actually significantly explodes. There's a training process called adversarial training. It's very expensive because it requires multiple additional gradient steps. And if we can get rid of this and just kind of look at what features it's looking at and correct these in some efficient way, then this would be a great way to achieve robust models for like maybe a fraction of the price that adversarial training requires. And we wanted to look at this and just do a little correlation study, because a lot of papers are out there saying that indeed this is the case. If you make your model see like a human, it becomes more robust. And these papers have achieved numerous orals at, I think, NeurIPS and CVPR. And unfortunately, for a lot of them, it's just not true. So they correlate only under very, very specific conditions. So what we did in this CVPR paper last year is we looked at 3 specific vision biases. So these are 3 examples where models behave differently from humans. We started with the texture bias, which shows you that models really look at textures and humans look at shapes. We looked at the critical band, which is like in frequency domain, the characterization of the channel that you're using to recognize an object. So the idea is that in frequency space, there's actually only a very narrow amount of information that the average human needs to recognize something. And for a model, this is significantly wider for some reason. And finally, there's also a high frequency bias. So when you kind of separate your image into a low frequency part and a high frequency part, the model tends to operate really well on the high frequency part, which usually is like mostly noise, and humans don't recognize anything here. And on the low frequency part, the model is doing quite bad, although humans still recognize the object. And so we took a bunch of models and we correlated their vision biases with their ability to generalize on 4 different benchmarks. So these are different data sets that we're basically measuring the accuracy on. One category of data sets is in distribution. So these images look pretty much exactly like the training distribution of the model. Then we have some robustness data sets, which just corrupt the images in some way. So these are still the same images, but just applied with some corruptions. Then we have conceptual changes. So instead of now having photographs, we might have sketches or paintings or cartoons of the objects. So this really probes for whether the model is able to like really understand what the object is, and then also adversarial attacks. And like the little caveat that we did here is that we controlled the architecture and the training data. In this case, it was a ResNet 50 and ImageNet. And this is important because we want to know, is the bias connected to generalization and not is just using more data connected to generalization, because we know that this is true. We also know that CNNs and vision transformers behave differently. So we kind of wanted to control for that and really fix the architecture and the training data such that we're only looking at the bias. And I'm not going to show you the results for all the biases because they're very similar. So what you can see here is like the shape bias. On the x-axis, we have the measurement of this, and a 0 would mean that the model is completely texture biased, and a value of 1 would be close to 100% shape bias, and this is where humans would be. And on the y-axis, you have the performance of the models for the 4 categories: in distribution, robustness, concepts, and adversarial attacks. And every point here is like basically one model. So remember, they're all ImageNet models, they're all ResNet 50s, they're just trained in different ways. You can ignore the color for today, it's just how they were trained. And the alignment, so the models become more human-like as we go towards a shape bias of 1. And what you can see is that for robustness and concepts, there is almost no correlation. It's quite flat. Sometimes, or actually the most robust models are the one with the least shape bias. For concepts, it kind of seems to increase a little bit, but then it falls off, and then there are a lot of outliers. For adversarial robustness, it might appear as if there is a positive correlation, but then you have a strong outlier which has a shape bias of over 80%, but it has like virtually no adversarial robustness. So there's no correlation here as well. And for in-distribution performance, it's actually like the complete opposite of what you would expect. As you make your models more like humans, they actually decrease in performance and they get worse. And overall, this is something we have observed for all of these biases that I showed you. There is like no silver bullet. So just because you fix one bias, it doesn't make your model magically more robust or generalized better. And the claims that were made in these initial papers are just flat out wrong, and they're tested. Or the statements are made purely based on correlations. And then if you test this a little bit more thoroughly, you will see that this unfortunately doesn't hold. Okay, so the talk today is about feature biases. And so far, I probably convinced you that feature biases are not very useful, at least for not for generalization. But I want to make the case on why it's still worth looking at it. So we have seen that there's probably not like one single bias that is useful to fix in terms of generalization. But I want to say that each of these is like a steering wheel. So maybe there's like a combination of all of them that gives you a better model. So we are only testing like higher shape bias, but what does that mean in other terms of biases or other aspects? We're never controlling for that. So there might still be like a perfect vision model that you can sort of tune, and then you get perfect robustness or generalization, but this is super hard to achieve. And it's not as simple as just fixing one little thing. However, even if that is not true, understanding what features a model is looking at kind of gives us some insights on how the model operates and what it's looking for. And one example is shown on the right. So this is obviously like a green apple, so a Granny Smith apple. And then someone put a piece of paper on top of it, which reads iPod. And if you show this image to Clip will tell you that this is an iPod. It will never look at the apple. It will never recognize that there is an apple, although it perfectly recognizes apples. But whenever you put text on something, Clip starts to read that text and completely starts to ignore whatever is behind it, or the actual object in this case, which is clearly not an iPod. So depending on your use case, you really want to understand what biases your model has, because otherwise you might run into effects that you're not, that you don't want to have in production. So, I mean, if your goal is to recognize apples, then it shouldn't be affected by text, for example. And lastly, I also want to say that there are actually some communities that are interested in building models that operate exactly like humans, not for the reason of robustness or generalization, but for other purposes. One of them is the neuroscientific vision research community. They obviously, like, for example, they're studying human vision, and so far they're doing this with human experiments. These are kind of expensive. Humans get tired. Like, it's super hard to get people even to test them. So if they can automate their research by models that operate like humans, that would be a great benefit for them. The second community that I recently learned about that is also interested in this is UX research. So they're testing like different kind of user experiences. And usually this also involves human trials. So humans look at, like, for example, some kind of new app or new website, and they tell you like how great it is. And if you could replicate what humans look at and how they kind of process information, then you can automate this as well. So this would be a great benefit for them. So, but for today, I want to like focus on the second bullet point, which is understanding what models do. And specifically, I want to talk about this paper that we just presented in Singapore a few weeks ago at ICLR, which is titled, "Can we talk models into seeing the world differently?" And this paper is about vision biases in multimodal large language models. So something like GPT-4 or the open source counterparts. So I was very honored to work with a lot of great people on this paper from all kinds of institutions, at the University of Siegen, MPI, MIT, and Google DeepMind. And so this is really a collaborative effort, this paper. And yeah, it was a lot of work, so I was very happy to see it accepted into ICLR. So before I kind of go into like the mechanistic perspective of these multimodal models and how they operate, I want to explain how can we even test whether a model has a bias for a specific feature or not. There are in general a ton of different ways. I like the behavioral testing. So the idea is you take two samples that are belonging to two different classes. So sample 1 belongs to class 1 and sample 2 belongs to class 2. And then you mix them together into a new sample, which is constructed from one specific feature from sample 1 and one specific feature from sample 2. And now this new sample now has two labels. It has a label for class 1 and for class 2. And depending on what your classifier looks at and what kind of feature it prioritizes, it will respond to you whether this is class 1 or class 2. So this is like a single label classification process. And if you do this over multiple samples, you can estimate the feature bias by just counting how often the model predicts, for example, class 1 over all the correct responses that it gives you. And if it's always telling you class 1, then it's probably looking at this feature 1 and not feature 2, or it's just at least prioritizing feature 1 over feature 2. To make this more concrete, let's look at the texture shape bias, which was introduced by Robert Garros in 2018. So the idea here is we're really looking at object-centric learning, something like ImageNet, where we have one object clearly centered in the image, and the goal is to recognize it. And the way we're constructing our test data set is we're taking two samples again, and from one we will copy over the texture, and from the other we will copy over the shape. So the cat gives us the shape here, and the elephant gives us the texture, which is like the elephant skin. And then we get a new sample, which is obviously this combination of features. And depending on what your classifier is now looking at, it will give you a different response, whether this is an elephant or a cat, or in other words, it will give you a shape or a texture response. And now to compute the shape bias, we just, again, count how often does the model predict shape, as opposed to all the correct answers it gives. And if we do this, we'll see that for humans, it's 96% of the time. So humans predominantly look at this shape information, and they kind of ignore texture, or texture is secondary for them. And if you do this with an ImageNet trained CNN, on the other hand, you will see that these models are strongly texture biased. So they kind of ignore the shape. They really prefer texture, and in this case, they would tell you that this is an elephant. Okay. But as I told you, we're dealing with multimodal LLMs, so these are not classifiers. So how do we apply our scenario to these models? And we came up with two approaches to do this. The first one is a closed vocabulary approach based on visual question answering. So the idea is we give the input sample to the model, and then we give it a list of all the possible labels. In our case, this data set only has 16 classes, so this is really simple. We just list all of the classes, we enumerate them, and then we instruct the model to reply with the label that it thinks fits most. Now, this assumes, of course, that the model is actually following our instruction. In our tests, we have seen a lot of models where this was not true, but we kind of filtered for the models that are working well in this case. There's one trick that we're doing here. We're forcing the model to not reply with the actual label, but we are forcing it to reply with the option key that corresponds to the label. And this is important because we only have 16 classes. Every option key is exactly one token. And since it's one token, we can not only get the answer, but we can also look at the distribution of confidence that our model has in each token. So basically, in this case, we have 16 classes. So we have everything from A to P. And for each of these characters or these tokens, we can look at the logit that the LLM assigns, and we can understand whether the model is actually seeing multiple things, or it's like insecure in its answer, or maybe it kind of sees both. So in this case, we have an elephant with an overlaid bottle texture. The question is, obviously the model is like giving us the answer that this is an elephant, but the question is it like maybe uncertain about this? Maybe it's like 51% elephant and 49% bottle, or does it like completely ignore it and just say, okay, this is clearly an elephant? Now, the second way we are testing models is an open vocabulary setting, which is more closer to what the models can do, because like if we do this VQA style, we're kind of artificially constraining the model to only respond with labels that we gave it to the model. And in open vocabulary, we do not impose such constraints. What we're saying is, okay, model, please describe the image, and it will give us like a caption of what it sees. So in this case, a collage of bottle caps in an elephant shape. And then for our bias testing, we need to convert this into a classification setting again. So what we're doing here is we're using a sentence embedding model, and we're embedding this description that the model gave us along with all the labels that we have, and then we just do zero-shot classification as in clip. And this gives us our single label response again, including logit, so we could also look at the confidence again. Now, in this case, the model gave us actually an answer which contains two labels, and the sentence embedding models, actually most of them are quite bad. So we're also using a second approach, which is just an LLM, another LLM, which we instruct to give us a list of all the labels that it detects. So in this case, it was tell us the label bottle and elephant is present in the description. The downside is here we no longer have access to this logit information. So for this setting, evaluation is a little bit harder. And so the first survey that we did is we measured this texture shape bias in both the scenarios that I just explained on different kind of VLMs. And I want to say, like, I'm going to show you a lot of results on the texture shape bias, but I want you to think of this as an example for any kind of feature bias that you have. So we're using texture shape bias because everything was ready for that data set, but you could also mix different kind of features and do the same thing. So we're testing a lot of VLMs here. As you can see, it starts with closed source models on the y-axis, including Gemini and GPT and the large Quen models, which are proprietary. And then we also have a lot of open source models, from InternVL to Lava to InstructBlip and a couple of others. And on the x-axis, we have the shape bias. So from left to right, it increases in the number of shape decisions that we have. And on the upper x-axis, we have the reverse direction. So this is like the texture bias, which is just 1 minus the shape bias. I also have a few reference models in red. So we have the Resonant 50 example, which is at roughly 22% shape bias. We have a clip zero-shot classifier, which is at roughly 60% shape bias. And we have the human performance, which is roughly at 96%. And then for every model, we're testing this captioning, so the open vocabulary, and the VQA setting, which is closed vocabulary. And what you can see is that most of the models cluster quite well. So all the responses are roughly between 60 and 70% shape bias. So they are significantly more shape biased than CNNs, but they're also more shape biased than clip models. So this is quite an interesting trend, in the sense that we see that models are becoming indeed more human-like. Whether that is good or not is a different question. We're also seeing that for a lot of models, like, it doesn't really matter whether we're using it captioning or VQA, the performance is quite stable. Of course, there are a couple of outliers to this, but overall, there's not like a huge difference between captioning and VQA. There are a couple of interesting outliers here. First one are these two models, which is QuenVL and UForm. They are the only models which are texture biased, and not strongly texture biased, but still more texture biased than shape biased. And these models are also example of models that perform very badly in VQA. So when we instructed them with this, give us the correct option prompt, then it would simply not follow that and spit out something completely else. So maybe there is a correlation between a high texture bias and a poor alignment during fine-tuning, but we haven't investigated this more thoroughly. Another interesting outlier is GPT-4. It's like the only model that, or like the only good model that sticks out. It's at roughly 50% shape bias, so it's like 50-50 in whether it gives you texture or shape. And in the beginning, I thought, okay, this is probably because GPT-4 is doing something completely different. By now, I'm more convinced that it was just trained on this data set that we're using, because this is a public data set and all the labels are public. So I think GPT-4 is just 50-50 because it has seen like the answers for this. But is even though that we kind of exclude GPT-4 like for the rest of the experiment, this gives us a little bit of hope because the other models are not 50-50, so it's like unlikely that it wasn't their training data. Okay, now let's take a look at how feature biases evolve in autoregressive VLMs. So whenever you connect a vision encoder to a large language model. Now, obviously, your inputs are a kind of image, so our test stimuli here and our text. And what you typically do is like you first have a vision encoder that transforms your input image into a token representation that is completely independent of the prompt. Then you tokenize your prompt, you convert the image tokens into the same dimensionality as the text tokens are, and so via a simple projection. And then you feed this into the LLM, and the LLM predicts to the next token. Now, there are two sources of bias here. The first one is the vision encoder. So the vision encoder itself already kind of extracts vision features, right? So this will have a huge influence on how or what kind of information is fed into the LLM. But the second part is the LLM itself, because the LLM operates on the vision tokens and the language tokens, and it kind of fuses them together, it projects them to some spaces, and it will have some kind of influences on this, and we don't really know what exactly it does, but it's very likely that it does a lot. And so the first question that we had was, is the full VLM behaving exactly like just the encoder in terms of the bias? And luckily for a lot of these VLMs, the encoder is available as a standalone zero classification model. In this case, it's typically CLIP. And during training, the VLMs actually leave this vision encoder frozen. So we can just measure the shape bias of the CLIP and from the entire VLM and just compare the results basically. And when we're doing this, we see that the change in shape bias can be positive or negative. It can sway by up to -10% to up to almost 8%, where the performance increases towards shape bias. And so this shows you that the full VLM behaves differently than just the encoder. And this is an important observation for vision processing. The other metric that we looked at is error consistency. So this looks at whenever the model is doing an error, is it making the error exactly like some other model would do? So in this case, we're again comparing the VLM and the CLIP encoder. And what you can see is that the error consistency is somewhere between 50 and 77%. So even when it makes errors, these errors are different from the vision encoder. So there's like a lot of differences here. And in summary, the full model does not behave like the vision encoder, even if the vision encoder is never changed, it's just connected to an LLM. So now we want to know, okay, since the full VLM behaves differently than the encoder, what is actually happening in the LLM? How does it arrive at its decision? And remember, for the VQA setting, I explained to you how you can get the confidence in an answer. So what we're doing is whenever the model gives us an answer, we're checking the confidence for the texture response and for the shape response, which I highlighted here in orange and blue. So the image shows you again the elephant with the bottle texture on top. Obviously, the shape in blue is elephant, so this is the token L, and then the texture Q is a bottle, so this would be the answer F. So in this case, we would look at the confidence that the model has in the token F and the confidence that the model has in the token L. We do this over all the answers, and then we try to understand, does the model really perceive both of the Qs, or is it like super biased? And we did this on multiple models, and the results that we're seeing is that indeed the model is very biased. It's not like 50-50 in its decision. When it makes a decision, it is highly confident in its decision, so it's assigned a probability of 100% to this token, and the opposite token is at 0%. And this applies equally for whenever the response is texture or the response is shape. So this shows you that the language model is actually the true source of the bias. The vision encoder feeds you some kind of representation, which is a little bit of flexible, and then the LLM goes ahead and says, okay, this is texture or shape. It completely ignores that there is also a different Q. And in fact, we checked the confidence for the second most likely token in all of these LLMs or VLMs, and it never belongs to the second Q. It's typically just a wrong response. So yeah, the LLM has a strong bias. This is actually very similar to discriminative models. So even if you train like a resonant classifier, the resonant classifier itself actually is not that shape biased, but the linear probe that you have on top, the classification head, is where the bias is coming in. And now, since the language model has such a strong influence, the question was like, can we just talk our model to changing its bias? Which means we're just played around with different prompts. So it's as simple as changing our neutral instruction, which is which option best describes the image, into shape biased and texture biased prompts, which are identify the primary shape or identify the primary texture. And then we kind of give it the list of options that it can pick from. The second thing we wanted to know is like, are there better prompts? And for this, we're using an external LLM as an optimizer. So we instruct this LLM to design new prompts that are more shape biased or more texture biased. And we give it access to prompt the VLM. So the LLM will just feed the prompt to the VLM. We kind of run the evaluation there, and then we feed back the accuracy and the achieved bias back to the LLM. And this is like an optimization loop, so this keeps running until we're satisfied. And that way we can actually achieve prompts that are even more shape biased or more texture biased than the handcrafted examples that we have. And yeah, so here are the results. We first tried this on Gemini Pro Vision.
Yeah. Previous slide. Which LLM were you using, and like was the LLM ever a part of the text encoder of the VLMs as well? So was there any commonality between the LLM used for this and the text encoder of the VLM, or were they two very separate things?
Always. So this was, and so this was a completely different LLM. I think this was at that time Mixtro, and then the VLMs typically used VQNA or something. So it's like a completely different thing. But there's a nice paper from DeepMind showing that even in that case, you can still use an LLM to optimize prompts for VLMs. I have to say we used a very simplified setting, so we just like let it pretty much guess a prompt, and then we would feed back the accuracy bias. There are many techniques that you can do to improve this further. I'm actually going to show you this in a second as well. So we ran this on Gemini Pro Vision. Back when we wrote the paper, this was Gemini Pro 1.0. By now, this will probably look a little bit different. And here I'm showing the performance with the handcrafted neutral prompt, the texture prompt, and the shape prompt. And the white star is the neutral performance. And we switch to the shape prompt, it gives us a more shape biased response. When we switch to the texture prompt, it gives us a more texture biased response. So of course, we kind of know that VLMs can follow instructions. This is what they're trained for. But it's kind of interesting to see that even with such a simple linguistic trick, we can switch the underlying low-level processing of vision features in these VLMs. And we repeated this experiment on many other models, so Quen, Lava, and InternVL. And what you can see is that this always works. So we're always kind of pushing towards texture or shape bias. But the range of how much this affects the model kind of depends on the model itself. So for Gemini, the range is not that huge. For InternVL, it's significantly larger. And we're also commonly observing that it's easier to make a model more texture biased than more shape biased. But this may be simply a fact because the model is already more shape biased, so it's kind of easier to switch in the other direction. We also did a thing where we tested synonyms. So in our manually designed prompts, we replaced the word texture with synonyms for texture, and we replaced the word or the term shape with synonyms for shape that we just got from a dictionary. And what you can see is that the performance clusters pretty well. So not only does the language model understand what texture is in terms of like understanding the word, it also seems to be able to correlate it correctly with the vision tokens among different ways of kind of formulating this word. And then in gray, we also have on two models the performance with our automated search, so our LLM designed prompts. And you can see here for InternVL, we're actually able to make a model which is quite strongly shape biased. So it's at roughly 70% shape bias. We can make it now texture bias. And I want to say that this optimization was constrained to never change the accuracy. So this is really flipping the bias internally in the model, or like the output bias, but not like making it forget texture responses or something like that. So it's really affecting the processing. We also refined this method. So as I just told Shashank, it's like a very simple method that we applied. We have a new paper out, which is called GLOVE. It's currently under submission at TMLR, where we refined this optimization technique. And I think if we would use GLOVE to optimize these prompts, we could probably even get a higher range. But it's still impressive that, for example, on InternVL, even with this simple optimization technique, we can get results that kind of steer this bias by up to 25%. And this is really something that comes from the language model. So obviously language severely influences like this low-level processing of vision features. And this is something that you only see in VLMs. So in discriminative models, you have to retrain them or you have to fine-tune them to change their biases. In a VLM, we can just switch the prompts. So it's really simple, it's cheap, and it's a very effective way of steering the processing in these models. Now, we also wanted to make sure that this is not only applying to texture shape bias, although most of the results are on that. So we designed a new data set where instead of conflicting textures and shapes, we're conflicting low and high frequency information. So what we're doing here is we have a blurry image of an elephant, which is the low frequency component, and we have the high frequency component of a truck, which is mostly like the edges of it. And we're overlaying this to an image. This image has now two labels again, and we can prompt our model to respond with the most likely label that it wants to assign to this image. And this data set, we call the frequency Q conflict, is also available on Hugging Face. So if you're interested in bias testing or you're interested in frequency regularization, there's like a lot of people working on that, then you can take that and use this data set to test your models. And in terms of results, we only tested two models here, InternVL and Lava Next. And once again, you can kind of see the neutral performance. And when we do our search optimization via the LLM, this gives us either a higher low frequency bias or a lower low frequency bias. The results here are not that great, so it's just a few percent here and there, but it's still significant. And to be honest, we didn't spend too much compute on these results. So I think if you would spend more time like finding a good prompt, then you could probably increase this bias here much stronger as well. Right. So in conclusion, this steering also is not limited to texture shape bias, or in fact, like any of the experiments that I just showed you are not limited to this texture shape bias. They can apply to any vision bias. There's one constraint, and that is if you have a separate vision encoder, as we had in our example, then this vision encoder needs to be able to separate the features. Like this is like the precondition of this. But luckily, most vision encoders that we train are able to separate most signals quite well. So this brings me to the summary and the end of my talk. I hope that I was able to convince you that it can be useful to understand what your model is doing. And this seems super obvious, but I had so many job interviews where people look at me like I'm crazy when I tell them about explainability. Or like at ICLR, I talked to like a couple of finance companies and I asked them like, do you actually understand what your model is doing, how it's trading? And the answer is typically no. People really look at the accuracy, the model works, great, job done. But when things go wrong, you really want to understand what your model is doing, what it's looking at. In computer vision, these are like the vision features. And there's a lot of research happening there. It's still a very emerging field. I can only recommend to kind of look into this more thoroughly. I also showed you how you can identify feature biases and VLMs via behavioral testing, so via these Q-conflicted samples that I showed you. We've seen that VLMs do not simply inherit their biases from their encoders, so the LLM itself is also a strong source of bias and kind of changes how models operate. And finally, I showed you that we can simply talk a model into changing its bias by just using a different prompt, so this is all natural language. On some models, we achieved a really high range of steerability, up to 25%. Just for reference, like there are people trying to optimize the shape bias in ImageNet classifiers, and they typically get like a few percent, like up to 5% plus or minus by using very expensive training techniques. And on VLMs, this is virtually for free. All you need to do is switch out your prompt for another one. Yeah, so this is the end. In the bottom, I also have a QR code which you can scan, which just takes you to the GitHub repository of the code base for this project. It has an implementation of all the VLMs together in one source file. So if you ever want to do experiments with VLMs, this can be convenient. It took a long time to assemble that. And it also contains the link to the paper, of course, and the frequency Q-conflict dataset. So with that, I thank you very much for your attention. And if you have questions, I guess we still have like roughly 15 minutes to ask them. So yeah, please go ahead.